Welcome viewers to the second segment of the fifth lecture for the online series of lectures for the course of General Relativity. Towards the end of the previous segment, we derived this explicit expression of the 0,2 tensor field that results in from taking the covariant derivative of one form. Now we are going to begin this segment with the expression of the covariant derivative of a general R, S tensor field. Will not provide the proof here. The proof is left as an exercise. So let me write down the general formula of the covariant derivative of a generic R, S tensor field here. Here is the formula. So T is the tensor field, underlying tensor field. It is of type R, S. So there will be R contravariant indices. Let me denote the contravariant indices with mu1, mu2 all the way up to mu4. Okay, and the covariant indices with mu1, mu2 all the way up to mu-s. Now we are going to derive this guy with, take the covariant derivative, and the covariant derivative index is rho. So we put a semicolon followed by a rho. Okay, and this is going to be equal to the partial derivative of the tensor component, the component of the tensor field, mu r, mu1 all the way up to mu-s, comma rho, meaning that we are taking partial derivative with respect to x rho. And then there is a plus sign here, and so there is a nice way of remembering it, the formula. So we first take the contravariant indices, and so replace the first contravariant index with a dummy index, okay, and then leave the other ones as they are, mu2 all the way up to mu-r, and we don't touch the covariant indices at all, mu1 all the way up to mu-s. Okay, and then we attach this connection coefficients here, gamma. Okay, and the one that was missing from this contravariant indices, we put it here. Okay, and this dummy index sigma gets contracted with this covariant index in the connection coefficient, and this covariant derivative index comes here. Okay. So now for the second one, see that we start the same way. So now the first contravariant index stays there, and the second one is replaced by the dummy index, and the third one stays there and all the way up to mu-r, and the covariant indices are untouched. And then again here the connection coefficient, and now the second contravariant index that we replaced with sigma comes here. Okay, and this sigma is contracted against this sigma here, sigma down here, and this covariant derivative index comes here then as before. Okay, dot all the way up to for the last contravariant index, we have this contribution mu1, mu2 all the way up to the last one gets replaced by the dummy index sigma here. Okay, and the covariant indices are untouched again as before, mu1 all the way up to mu-s, and then this connection coefficient comes here, and this the last contravariant index comes up here, and this sigma is contracted against this sigma down here, and the covariant derivative index rho is down here. Okay. Now we have to deal with the covariant indices in this business. So the first one comes with a negative sign, okay? And in fact, all the terms concerning the covariant indices they all come with negative signs, okay? So here, the contravariant indices are untouched, mu1, mu2, all the way up to mu r, okay? And the first covariant index is replaced with sigma, okay? And the second one all the way up to last one remain the same. Okay. Now I attach the connection coefficient here, and that dummy index sigma is contracted, is being contracted against this index up here. Okay. And now the first covariant index that was replaced with sigma comes down here, and the covariant derivative index rho is lives down here. Okay, so that was the first term contributed by the covariant indices. For the second contribution of the covariant indices is as follows. So the contravariant indices stays the same as before. Now the first covariant index stays the same, which is mu1, the second one being replaced by sigma, the third one stays the same all the way up to nu s, and now the connection coefficient that gets attached with this expression has sigma, which gets contracted with this sigma down here, and now is the turn for nu2 down here, and the covariant derivative index is down here. Okay, so all the way up to the last contribution from the covariant indices is as follows. T, as before, the contravariant indices stays the same, mu1, mu2 all the way up to mu r, and then mu1, mu2 all the way up to the last index, and the last index is getting replaced with sigma now, and the connection coefficient here has sigma up here, so that it gets contracted with this sigma down here, and finally we have nu s coming down here, the last covariant index of T, and the covariant derivative index rho is down here. Okay. So this is easy to remember, and this is the general expression of the covariant derivative of a general R, S tensor field. Okay, the proof is left as an exercise. Prove it. Exercise. Okay, good. Now it's time to talk about torsion freeness of connection, of an underlying of the underlying connection. Okay, that the manifold is equipped with. Okay. Okay, so let me provide you with the notion of torsion freeness of a connection. Torsion freeness Okay, so let us recall the second equation when we were trying to derive the expression of nabla xy, it's a vector field, and the component of this vector field is given by equation number 2, right? And it was denoted by, we have seen that this is denoted by y mu semicolon nu x nu. This is the 1,1 tensor field, right? Nabla y mu nu. Okay, so now let us try to write down this expression in a given coordinate basis. In a coordinate basis, we can write this expression x nu y mu semicolon nu minus y nu x mu semicolon nu. Okay, this is good. And we know the expression of this guy, right? We have derived it earlier in the first segment, and let us replace this guy with that expression, which is equal to x nu y mu comma nu, the partial derivative with respect to x nu, the partial derivative of y nu with respect to x nu, plus gamma mu rho nu y rho. Okay, then we have y nu x mu comma nu plus gamma mu rho nu x rho. Okay, so let us play with this expression x nu y mu comma nu after getting rid of this bracket, plus gamma mu nu rho x nu y rho minus y nu x nu comma nu, and then minus gamma mu rho nu y nu x rho, y nu x rho, from which we get the following, which is the same as x nu y nu comma nu minus, I take this summand first, y nu x nu comma nu, then I have plus gamma mu rho nu x nu y rho, and then finally I have this expression, right? Gamma mu. What I'm doing here is that I'm just interchanging in this case rho with mu, so that I have nu rho here and then rho mu here. Okay, good. Now erase this top part. So from here we have this guy is nothing but the component of this vector field. The commutator of two vector field is again a vector field, and the component of that vector field that resulted after taking the commutator is given by this expression that we have seen earlier. Okay, so this is x, the commutator of x and y, mu, and this remaining part is as follows: 2 times gamma mu. It's an so symmetrization. Well, anti-symmetrization here. This leads to this expression. This anti-symmetrization leads to this expression where this bracket is defined as 1/2 gamma mu rho nu minus gamma mu nu rho is the same as gamma mu, the bracket, rho nu. Okay, this is our equation number 6. Let me erase this part now. This bottom part I am erasing. Okay, good. Now I want you to reconsider equation 5 that we derived in the last segment. Okay, let me write it for you here. Equation 5 was the covariant derivative of a one form gives us a 0,2 tensor field, and which is the components of which are given by the following expression: eta mu comma nu minus gamma rho mu nu eta rho. Okay, so we have seen that there is another way of writing it, which is nabla eta mu mu, right? Because it's a 0,2 tensor field. So equivalently, it can be written like, we can take this nabla in the physics literature. We see that this nabla is brought to the covariant derivative, so that it signifies that this nu comes out of the action of this covariant derivative operator. This is a convenient expression. It will help us do what we want to do now. So let us take a special case of one form, which is an exact one form given by eta equal to df, where f is a smooth function on the manifold. Okay, and see how then this expression looks like. If I choose eta to be df, this exact one form, then this is given by nabla mu df mu, right? And we know that the components of this exact one form df are the components of the gradient, right? In the beginning of the first segment we have discussed it. So this is nabla mu del f by del x mu, and we all know that the partial derivative coincides with the covariant derivative when acting on a function, right? So this is nothing but nabla mu f, which is f semicolon mu mu. successive application of two covariant derivatives on a scalar function. Okay. So let me write it down here. For scalar functions, nabla mu and del mu coincide. Okay, so let me erase everything. Well, now you see that this was the expression I needed. Equation 5. Eta mu comma nu minus gamma rho mu eta rho. Okay, so I'm considering the special case when this one form is given by this exact expression, exact one form. Then then the left hand side, we have seen that that left hand side becomes f semicolon mu, and the first term, so the first term on the right hand side becomes eta mu comma nu is equal to del x del by del x mu. It comes from mu. It comes from this index, and here we have df mu, right? Or eta mu is df mu. Df mu is equal to del by del x mu, and df mu is del f by del x mu. Well, what is it? It is f comma mu, successive application of partial derivatives on the scalar function. For the second term on the right, this one, for the second term on right hand side becomes, for the special case of eta being equal to df, eta rho is df, this component of this one form is the partial derivative, right? Partial derivative of x with respect to x rho, which is just f comma rho. So this becomes, for the case of eta equal to df, f semicolon mu to be equal to f comma mu minus gamma rho mu f comma rho, right? We all know from our basic knowledge of multivariable calculus that f comma mu is the same as f comma mu, right? They commute with each other. But in general, we see from here that the second covariant derivative don't commute after the interchange of the indices, right? In general, not equal to f semicolon mu. In general. Okay, because see that this is f semicolon mu and F semicolon nu mu is going to be given by F comma mu mu minus gamma rho mu mu F comma rho. Therefore, half F semicolon mu mu minus F semicolon mu mu from these two expressions we have negative 1/2 gamma rho mu mu minus gamma rho mu mu F comma rho. Therefore, see that this is nothing but according to the definition of antisymmetrization bracket, we know that F semicolon bracket of mu mu is equal to negative gamma rho bracket mu mu F comma rho, which again tells us that this generally is not zero. It's zero only when this is zero, right? And this is zero when they commute with each other. So we conclude that F semicolon mu mu is the same as F semicolon mu mu if and only if gamma rho mu mu is the same as gamma rho nu mu. That is gamma rho bracket mu mu is equal to 0. This is the situation we say that the underlying connection is torsion free. Okay. So we say that if this holds, then the underlying connection, if the two covariant indices of the underlying connection coefficients commute with each other, we say that the underlying connection is torsion free. Okay, and then the second covariant derivative of a scalar function is commutative. Okay, good. So let me erase everything. Now we know what it means by torsion freeness of a connection. Now get back to equation 6. So let me write it for you if you don't recall. Equation 6 was as follows: x nu y mu semicolon nu minus y mu x mu semicolon mu was equal to the commutator of x and y, the vector field, plus 2 times gamma mu bracket rho nu x nu y rho. Okay. Now and we know that this is nothing but nabla x y mu, right? And what is this? Nabla y x mu. So when the connection is torsion free, we have nabla x y mu minus nabla y x mu equal to nabla x y minus nabla y x mu, right, is equal to the commutator of the two vector field x and y. Okay. When the connection is torsion free, then this holds. Therefore, we have proved the following lemma. We have the following lemma, which states that for a torsion free connection, if x and y are vector fields, then nabla xy minus nabla yx is just the commutator of the two vector fields that we have found here. They are equal, right? Good. Now a small remark which is also important. Which states that we just saw that if the connection nabla is torsion free, the second covariant derivative of a scalar function commute. Okay. We just saw that if the underlying connection nabla is torsion free, then the second covariant derivative of a scalar function commute. But the second covariant derivative of a higher rank tensor field in general do not commute. Even the connection is torsion free. Even the connection is torsion free. Okay, this is very important. Okay, so now we'll have metric connection defined. Okay, and then we'll state and prove fundamental theorem of Riemannian geometry. And finally, we'll deal with a finely parameterized geodesic. We'll discuss the concept of parallel transport. Okay, so let me define metric connection first. So let me erase everything because it's not related to what we have done so far. So metric connection So far we never needed the manifold to be equipped with a metric. It was done for a general differentiable manifold, okay? But now we need to equip our manifold with a metric. So now comes the notion of a manifold with metric. On a manifold with metric, theorem. Let M be a manifold with a metric G there exists a unique, it is important to note that it's unique, there is only one. There exists a unique torsion-free connection, and it also exists. There exists a unique torsion-free connection nabla such that the metric is covariantly constant. The metric is such that the metric is covariantly constant. That is, nabla G is equal to 0, which means that G mu semicolon rho is equal to 0. So this condition is called metric compatibility in some literature. Metric compatibility. Okay, so if this metric is covariantly constant, this connection is called Levi-Civita connection or metric connection. Okay, so let M be a manifold with a metric G. There exists a unique torsion-free connection nabla such that metric is covariantly constant. Okay, and this connection has a name, is called the Levi-Civita connection. Levi-Civita connection. Okay. So this is also known as fundamental theorem of Riemannian geometry. Okay. So here is the outline of, so this is what we want to do. This is the plan of the proof. We are going to first assume that such a connection exists on the manifold, and we are going to prove the uniqueness of such a connection, and later we'll prove that it exists. Okay, and hence it's proven that it exists and is unique. Okay, so that's the plan of the proof. So let's first assume that such a connection exists on the manifold, and we are going to prove that it's unique first. Okay, but even before that, we need a formula how the connection works, how the connection acts on vector fields. We need expressions like this. Okay, so that is given by Cauchy formula. We are going to find it first. So let's start. the proof. Let x, y, z be three vector fields. Then x acting on g, y, comma, z, right? You see that g is a 0, 2 tensor field and y and z are vector field. So this is going to be a scalar function, and x acting on that scalar function will spit out a new scalar function. Okay. So, well, this is nothing but nabla x, g, y, comma, z, right? From the property of covariant derivative. We know already that. Because we already know that this metric compatible connection exists on the manifold. And this is going to be equal to, by definition, nabla x g. What is this nabla x g? This is going to be another 0, 2 tensor field, right? Covariant derivative of g along this vector field x is going to give us a new, covariant derivative of this tensor field g along this vector field x gives us a new, metric. So nabla x g is a 0, 2 tensor field, and that is acting on y, comma, z to give a scalar function, plus g acting on nabla x, y, comma, z, which is again a function, scalar function, and then g acting on y, comma, nabla x, z is again a scalar function. Okay? And this goes to 0 from the metric compatibility condition, and this gives us what? G of nabla x, y, comma, z plus g of y, comma, nabla x, z. This is our equation number 7. Similarly, exactly repeating the same thing, we show that z of g of x, comma, y is going to be equal to g of nabla z x, comma, y plus g of x, comma, nabla z y. This is our equation number 8. And finally we have y g of z, comma, x to be equal to g of nabla y z, comma, x plus g of z, comma, nabla y x. This is our equation number 9. Okay, now 7 minus 8 plus 9 will give us the following. So x, g, y, comma, z plus 9, y, g, z, comma, x minus z, g, x, comma, y. Okay. So you do some manipulation to get the following: g of nabla x, y plus nabla y, x, comma, z. You also use the property of the properties of a connection listed in the beginning of the first segment, plus g nabla x, z minus nabla z x comma y plus g nabla y z minus nabla z y comma x. Okay, so let me erase this top part. This is our equation number 10. Okay, now the torsion free condition implies the torsion free condition implies nabla x y minus nabla y x is equal to the commutator of these two vector fields x and y. Therefore, this expression x of g of y comma z plus y of g of z comma x minus z of g of x comma y is going to be equal to, so pick up the first expression here, first summand, and apply this torsion free condition here. See that you can replace nabla y x with nabla x y minus commutator of nabla x nabla y x as nabla x y minus commutator of these two vector fields, right? This is what you can do, and if you do that, here you will arrive at g of 2 nabla x y minus commutator of these two vector fields, right? Sorry, I think I missed out this this what was that? I think I missed out this this z, right? So bilinear form, so that z has to be there. Okay, good. So this is the first summand. For the second one, nabla xz minus nabla zx is going to be the commutator of these two vector fields x and z, and then comma y, and then finally for the last summand it's going to be g of the commutator of y and z comma x. Okay. Good, which is equal to, by using the property of the metric tensor field, since it's a 0, 2 tensor field, and so we can take this 2 out, and we have g nabla x y from the linearity. We can write it as minus g x, y, the commutator of x, y, comma, z minus g of z comma x. We had x comma z here, so we have minus z comma x comma y, and then finally we have plus g y comma z x. So finally what we have this formula, right, which is called Cauchy-Joule formula. G of nabla x y comma z, we bringing it to the left hand side, is going to be equal to, or we keep it on the right side, right, and bring everything else on the left hand side, and then divide both sides by 2 to obtain the following: 1/2 x of g of y comma z plus y of g of z comma x minus z of g of x comma y, then plus g of the commutator of x, y, comma, z, and then we have total 6 contributions. We have written down 4 of them. G of z comma x comma y, and finally minus g of commutator of y and z comma x. This is equation number 11, and it's called Cauchy-Joule formula. It's a very important formula from differential geometry. Cauchy-Joule formula for the Levi-Civita connection. Okay, let me erase this bottom part now. Good. So we have derived Cauchy-Joule formula. Now it's important to note here that the non-degeneracy of the metric tensor field implies the uniqueness of nabla from the Cauchy-Joule formula. Non-degeneracy, let me show you how. Reci of G implies uniqueness of nabla. It is important. It is not provided in the lecture notes, so I want you to follow this closely, okay? Or you can derive it by yourself, but it's a very small argument. So say that we have another connection, another torsion-free connection on the same manifold, which we denote by nabla prime, okay? So for the same 3 vector fields x, y, and z, we can work out this nabla prime x, y, right? In the same way we did before. And then on the right side of this equation number 11, we see nowhere nabla appearing, right? So we'll have this, since we are using the same 3 vector fields, we'll have the same right hand side on the right side, okay? And from which we will have the following: G of nabla x, y, comma, z minus G of nabla prime x, y, comma, z to be equal to 0. Now, using the linearity of this thing, G, since it's a bilinear form, we arrive at nabla x, y minus nabla prime x, y, comma, z to be equal to 0. So it's true for all z, right? In the because the 3 vector fields that we started with were fairly arbitrary. So for all z in the space of vector fields on the manifold. Okay. But from non-degeneracy of the metric tensor field, we know that if this is the case, if this is equal to 0 for all z in the space of the vector field of the manifold, then it has to be identically equal to 0, which means that nabla x y should be equal to nabla prime x and y. Since x and y are arbitrary vector fields, these two connections should be the same. Okay? This proves the uniqueness of the torsion-free connection that exists on the manifold. Okay, this is how we prove the uniqueness of the connection of Levi-Civita connection. If it exists, we are yet to prove that it exists. Okay, before we prove the existence, we'll try to find an explicit expression for this connection coefficients lambda mu rho, okay, and show that they are precisely the Christoph symbols that we have derived by variation principle, by maximizing the proper time in earlier lecture, in the last lecture. Okay, so that we'll do in the third segment of this lecture. Okay, thank you for attending the second segment.